I'm Katsumi. Today, I'm going to talk about writing suite without an operating system. Some of you might be thinking this is a very specific topic. Don't worry, it's about how software works. We just use a microcontroller because it lets us see everything. Everything we cover today also happens on your Mac and iPhone. It's just hidden. Today, we reveal it. So let's get started. What happened before our app started running? Let's build it from scratch in Swift and see how it works. When we write an iOS or macOS app, we just put @main on a struct. The OS has already done all the setup. Display, networking, everything is ready to use. But what if there is no OS? Then you have to build all of that from scratch. In this talk, I'll cover two things. First, what it takes to reach main function. On bare metal, there's no OS, so you build the foundation yourself. Stack setup, memory initialization, everything needed to call your first function. Second, what comes after main function? In iOS, frameworks gives you one loop and threads. Here, you build those yourself too. By building these with our own hands, we will learn how software actually works beneath the layer the OS normally hides from us. So where do we start? On a Mac or PC, the OS is too complex to replace. We want a chip simple enough to build everything from scratch. The hardware we are using today is the Raspberry Pi Pico. It has an ARM Cortex M0 Plus processor, 264 kilobytes of SRAM, 2 megabytes flash. It's a tiny microcontroller you can get about $4. The sample code is available on GitHub. Everything is written in 100% Swift, no C code at all. Let me show you the overview. Let's see what it takes to get from power on to main function. There are 5 steps. We'll talk through each one. Starts from bootloader built into the chip. It loads the first block of the code from flash. Then, flash configuration, which sets up the flash memory so the CPU can execute from it. Then the vector table setup. The vector table is a list of addresses the CPU reads at boot. Then memory initialization, which prepares global variables and static properties for use. And finally, main function. Before we dive in, one important fact, all a CPU can do is read and write memory. Code execution, displaying something, hardware control, everything is done through memory read and write. Same operation, just different addresses. Mapping hardware to specific memory addresses and control it through read and write. This is called memory mapped I/O. The address is different, but the operation is always the same. Just read and write memory. On macOS and iOS, the mechanism is exactly the same, but the OS protects hardware registers from user application. Your app calls the framework asks the kernel, and the kernel driver accesses the registers. On bare metal, there's no protection. You access the register directly. Same mechanism, just different operator. Let's look at the let's look at how the boot process is implemented. Since the CPU can only read and write memory, the boot code needs to be placed at the specific memory locations. The first two things the hardware needs are boot2 and the vector table. Boot2 configures flash so your program can run from it. The vector table tells the CPU where the stack is and which function to call first. Both are called directly by the hardware, so they must be placed at the fixed memory addresses. How do we place code at the fixed address in Swift? Swift has attributes that let you control where data is placed in memory. When building source code into non-executable, the tool that decides the actual memory layout is the linker. The at section attribute tells the linker to place the data at a specific address. The name you give becomes the label the linker uses to decide where in memory it goes. The at used attribute prevents the compiler from stripping them out. Nothing in your Swift code references them. They are only referenced by hardware. So the compiler sees them as unused and would normally remove them. And the at C attribute on the reset handler gives it a C calling convention, so the hardware can call it. These are attributes you'd rarely use in an iOS app or macOS app, but here they are a bridge between your Swift code and the hardware. The linker script is what tells the linker where to place each section. The linker follows these instructions, arranges the object, and fills in the final memory address in the binary. Let's look at what's inside. It defines two memory regions, flash and RAM. Then, in the section block, it instructs the linker to place boot2 at the start of flash and vector into text, which is also in flash. Let's look at what the vector table does. It sets up two things. First, the stack pointer. It sets the stack pointer to the address at the end of RAM. The stack grows from there toward the lower address, so by starting at end, it has a full RAM to grow up into. Now the stack is ready. With the stack available, function now can be called. The hardware first reads entry 0 to set up the stack, then it reads entry 1 and calls the function there. That's the reset handler. This is the first function the hardware calls. The hardware called reset handler from entry 1 of the vector table. A Swift function has been called. That means we can now call more Swift function and continue from here. We've finally reached main function. Inside this reset handler, you call application.main function yourself. In iOS, the system calls the main function for you, but on bare metal, no one does that, so you have to call it yourself. From here on, you are in the Swift world. Let's write some code inside the main function. In embedded programming, the first thing you always do is blink an LED. To blink an LED, we first enable the GPIO peripheral, then configure pin 25 as a GPIO output. Then, in a loop, we write value to a register that flips the bit for pin 25. Since it flips a bit each time, the same operation alternates between on and off. All of these operations are memory mapped I/O we talked about earlier, just by writing a value to a specific memory address. An LED physically turns on and off. We just run switch functions on bare metal and control via hardware. Before we move on, there's an important detail. Look at this line that toggles the LED. We are writing the same value to the same addresses on every loop iteration. A normal compiler will look at this and say, you are writing the same thing to the same place. I can remove all but the first one. But each write to a hardware register has a side effect. It physically toggles the LED. If the compiler removes them writes, it also removes the side effects, and the LED stops blinking. To prevent this, the register struct uses volatile mapped register. Volatile tells the compiler that every read and write to this address has a real effect and must not be skipped. And the order of these access must be preserved. For example, you have to enable paper before configuring it. If the compiler reorders those writes, the hardware won't work. So the volatile package is needed. Now, look at the code we just wrote. It's full of magic numbers. It's hard to tell what each address means. We want to replace the magic numbers with named constants using global variables or static properties. Let's replace them with named constants using global variable and static properties. And this code won't actually work yet. On bare metal, global variables and static properties contain undefined values right after power on. You have to initialize them yourself. Before calling main function, you need to properly initialize the memory sections. Global variables and static properties are compiled into sections in RAM, not RAM. At startup, they need to be expanded into RAM before they can be used. We have to write this expansion process ourselves. Which region of RAM needs to be initialized? The linker determines the boundary addresses. To access them from Swift, we use the @extern attribute to reference the linker symbols. This gives us the actual addresses that the linker assigned to each boundary. Here's the implementation. It's just two while loops. The first copies initial value from ROM to RAM. The second zeroes out the remaining region. It uses the address we got through the @extern attribute to know exactly which range to process. We add this initialization function to the reset handler by initializing memory before calling main. Global variables and static properties get their correct values. The code with named constant that didn't work before now works correctly. Let's take a moment to compare that we have covered so far with iOS. On iOS, the ILD loads libraries, the runtime initializes, then main runs. Globals are auto-initialized, stack is set up by the OS. But on bare metal, we do all this ourselves. Different foo, same what. From here, you can write mostly regular Swift. But there's no run loop or threading provided by UIKit or Foundation. You have to decide how to structure your application, execution yourself. In this talk, I'll introduce 3 patterns: super loop, cooperative scheduler, and the hybrid combining the scheduler with hardware interrupts. First, the super loop. The structure is very simple. After initialization, you just execute tasks in sequence inside the infinite while true loop. This is essentially a giant state machine. Everything lives in one loop, and every task runs every iteration. For simple applications, this works fine. Let's see a real example. This is what's called the leverless or all-button controller for fighting games, and it's actually built entirely with the super loop. That might be surprising, but the application job is simple enough. With the buttons, send the states over USB, every task completes instantly since it's just reading and writing registers. So running the loop as fast as possible is all it takes. There's no need to manage multiple tasks running at different intervals. If a button is pressed, send it. If not, do nothing. It looks event-driven, but it's really just polling. That's why a super loop is enough. Let's look at the code. This is actual code from the game controller. After initialization, it polls buttons, checks USB status, and responds to the host requests over and over. Every task is just reading and writing registers, so it completes instantly. There's nothing no wait for, so running the loop as fast as possible it all takes. In a super loop, every task runs on every iteration of the loop. But what about building something like Tetris? You need game logic, rendering, music, and button input, all with different timing requirements. Managing all of that in single loop means a huge amount of state to keep track of. The cooperative scheduler solved this by splitting tasks. You register each task its own interval, game logic runs every 60 milliseconds, rendering runs every 60 milliseconds, and music advances every 8 milliseconds. Each task manages its own states independently, so changing one doesn't affect the others. The code's much easier to maintain, but the cooperative scheduler has a limitation. The execution model is fundamentally the same as a super loop. Tasks run at a time, and the task cannot be interrupted until it finishes. If the rendering task takes 25 milliseconds for I2C display transfer, the music task has to wait. The music can never play faster than the rendering allows. The hybrid approach solved this by moving time-critical tasks to hardware interrupt. Music runs in cyclic interrupt that fires every millisecond. Regardless of what the scheduler is doing, button input has captured by GPIO interrupt by the instant button is pressed. The hardware forces current task to pause, handles the interrupt, and resumes where it let off. The scheduler still manages game logic and rendering, but music and input are no longer held hostage by heavy tasks. This is Tetris built with the hybrid scheduler. Notice that the background music keeps playing smoothly even during screen rendering. The music runs on a timer interrupt, so it stays on time no matter how heavily the rendering is. And when I press a button, the piece responds instantly. Button input is handled by GPIO interrupts, so nothing is missed. All of this interrupt entirely in embedded Swift. Which pattern to use depends on what you are building. A game controller just pulls button and sends USB reports. Every task is instant, so a super loop is enough. Tetris needs smooth music and instant button response during heavy rendering, so hybrid approach is the right fit. The key is to pick a pattern that fits your application's requirements. Let me wrap up. Behind at main, there's a 4-layer setting up the stack, initialize memory, preparing the runtime. With embedded Swift, we can write all of it in Swift. Past main, it's the Swift you know. Swift is a well-balanced language. It can control hardware results directly, and it can build applications just as easy and safely. From the lowest level to the highest, all in one language, writing everything from scratch, seeing how computers actually work. And above all, writing everything yourself is just fun. I hope you'll give it a try. Thank you for listening.